Okay, guys, welcome to this week's statistics seminar. Today we have Dr. Douglas Nychka from the Colorado School of Mines, and his research interests include nonparametric statistics, statistical computing, spatial statistics, and spatial designs. Today, he would like to talk about something on the learning of a stationary covariance. So let's welcome Dr. Nychka. Please go ahead.
Okay, great, thanks. I'm pleased to give this talk. It's the only downside of this is that I really wish I was there in person. I love visiting your department. And it's just sort of sad that we have to do this over the internet. But anyway, okay. So as I said, please interrupt me if you have questions, and we'll just sort of see how this goes. Okay, so this talk is a fairly simple idea. In recent years, what I've gotten interested in is trying to do more standard spatial analysis more quickly. And so, trying to get a big data set analyzed on a laptop, trying to find shortcuts and approximations. And so I guess you can think of this in that vein. Okay, so let's see here. Okay, so I'm just going to give you a little bit of a motivating example. Talk about the kind of data we're going to look at, the spatial problem. Try to give you a bit of an introduction to neural networks, and in particular convolutional neural networks and also deep nets. We'll see how those work for approximating maximum likelihood estimates, and then we'll try it out on this climate example. This is the first time I'm just learning about deep nets as I do this research. I hope that I'm explaining it coherently, but go ahead and stop me. As you learn an area and go through it and try to give talks on it, it takes a few times to sort of get that right. And so I'm hoping that this will be clear here. All right. So, well, us old guys actually have all these books in our offices, and one of these is a handbook of mathematical functions and tables, and this was a big effort by the government, and I think the Bureau of Standards at that point to put together. But if you go into that, there's all kinds of tables of different special functions and tables of logs and sines and cosines and everything. But part of that is the approximation to the normal CDF. And so if you go down to this formula 7.1.26, we see that the normal function, their notation is the error function of x. We see that that's the approximation here is 1 minus this 5th degree polynomial times an exponential. And this 5th degree polynomial is actually a rational function. It's 1 over 1 plus p to the x. And here are all the coefficients that you have to plug in. Now, what's amazing about this formula is it's accurate to about 7 digits to approximate the normal CDF. Fast to evaluate, no numerical integrations, it's just sort of ready to go. And the point here is that tremendously useful. Why this works, I don't know. I suspect the numerical person that devised this had some strategies, but I suspect some of this was a little bit trial and error to sort of get this to work. So we have this approximation and we use it in our codes. It works fine. We take it for for granted. And of course, it's much faster than, say, if we worked out the integral numerically. Okay, so what's this talk about? What I'm going to use is neural networks to approximate maximum likelihood estimates. And just like that example I just gave, even though that approximation looks sort of crazy, we know what we want to compute. We want to compute the normal CDF. In this particular example, I know what I want to compute. I want to do spatial data analysis, and I want to find the maximum likelihood estimates for some covariance parameters for the spatial process. Similarly to that example from Abramowitz and Stegan, the approximation works, but it's going to stay mysterious. And that's sort of part of the baggage that we get with working with these neural networks, is that they're tremendously flexible and have lots of potential, but why they're successful is often a little bit mysterious. Okay, so I always like to start with the data that motivated this. And so let me go ahead and do that. So what you're looking at is eight climate fields out of 30. We can think of each of these fields as essentially independent realizations from a climate simulation. What we're looking at here is the variation in what we would call climate sensitivity, temperature sensitivity. So these are not temperature fields. They're a sort of derived quantity from it. And the interpretation here is, let's look at this part, and we see this big red spot up in the boundary between the US and Canada. So that's about 0.5. And the interpretation here is this is related to how sensitive that region is due to a 1 degree rise in global temperature. So I've already subtracted the means out of these. What this is indicating is that for this particular climate simulation, this particular area is much more sensitive to a change in global temperature than, say, maybe other areas. For example, this area down in the Southwest. If you're trying to do climate impacts and want to understand how the climate's going to change locally, say for your region, it's usually not feasible to run an entire climate model on a supercomputer for months to try to get an idea of that. What you'd really like to do is get to these fields directly, just to understand what the variation is in the sensitivity of your local area, or to try to understand the sensitivity in your region of the country to changes in global temperature. Global temperature is typically much easier to simulate. So you would do that with a simpler model and then use those global temperature projections to try to come out with this. So that's part of the motivation here. Specifically, what we want to do as statisticians, or sort of more recently, I pitch myself as a data scientist, because somehow people seem to understand what a data scientist does, and they've never quite understand what a statistician does. So as a data scientist, our problem is we would like to create a statistical model for these 30 fields, which involved quite a bit of computation on a supercomputer. We're going to create a statistical model that is much more efficient to simulate. So we're able to simulate many more replications of these fields than 30. And so that will allow someone studying climate impacts to look at more extreme events, be able to work with simulation sizes that are much larger than 30. And in fact, when this emulation is done statistically, you can just generate thousands of these fields, and they're actually very close to sort of what the original 30 ensemble member looked like. Okay, so getting specific here about what our goal is. That area over North and South America, the model output is about 13,000 grid boxes. What we would like to do is fit a non-stationary covariance function to that. And the way we're going to do that is take a window that's 16 by 16 grid boxes, move that across the domain. So basically almost all the grid boxes are the center, are close to the center of this 16 by 16 window. Within that window, we're going to estimate a spatial covariance for that, and just keep track of those. So the goal here is we want to move these windows across all the grid boxes. So essentially, we're going to have 13,000 separate maximum likelihood problems. They're all fairly small. They're 16 by 16, so we only have 256 observations for each of these, but we have a lot of them. And maximum likelihood itself is a little bit computational intensive. And so the big idea here, the big goal of this is that we want to do these fast. Let me just speak to this blue point here. So you say, okay, so we're going to estimate these spatial covariances for all these different grid boxes, basically the correlation range and the variance of the process and the variance of possible white noise. What are you going to do with these? Well, this is the final step in this analysis, which I'm not going to talk about today, is we're going to take each of these local estimates and basically encode them into a global non-stationary model. And one way to do that is to use basis functions. And we have an approach called lattice-Krieg. That's in R. That's one possibility. The other possibility is to use the kind of sparseness ideas that Matthias has worked on, working off the Vecchia approximation. That's also a possibility in terms of working with a very large covariance in a way that's it's computable. Okay, so we're not going to do the blue point, but let me just mention that final step is really what makes this into a statistical emulator. What I want to talk about in this talk is really this second point. Estimate a spatial varying covariance function by fitting covariances to small windows. So what we're going to do is we're going to train a neural net, a convolutional neural net, or we're going to use a dense net on the variograms instead of doing the maximum likelihood directly. Now, you might ask, well, if you can find these by maximum likelihood, why are you going to the trouble of fitting a neural net to do this? And the answer is that due to the way neural nets are structured and the way they overlay onto sort of laptop and computing node hardware, they can be computed much more quickly. And in fact, the overall result of this talk is we're able to sort of approximate these maximum likelihood estimates accurately and get a speed up of over 100. And I think even we can probably push this to be several hundred if we wanted. I'm just trying to be conservative here. Now, what I found is that when you have a computational method and it runs 100 times faster than what you're used to, you tend to think about doing things differently. For example, if we can estimate these parameters quickly on the order of minutes, we're going to have a very different approach to building models for non-stationary covariances for these fields. We're going to feel much more willing to sort of try things and test out different models, rather than the case of having to run this and having a few hours and getting something back. So it really changes how you view data analysis. Okay, so here's the covariance function that we're fitting. It's the Matern. We're going to pick, so the Matern has it has 3 different parameters here. It has a variance out front, which just controls the variance of the process. It has a smoothness parameter that controls the differentiability of the process. And I want to say in all these examples, I'm just going to peg that at 1. So sort of a compromise between a really rough process and something that's very smooth. The third parameter it has is this thing called theta, the correlation range. And that basically just controls how far points, as they're separated by a certain amount of distance, their correlation. And I might slip into calling theta the range parameter here. Okay, so that's our covariance. Let me fill this out and talk about our spatial model. This would be that climate sensitivity that I'm showing you. It's going to be related to a smooth field over space. And then in spatial statistics, we like to add a white noise component onto that. It's a little bit of an approximation. It's a little bit of being lazy here. But it's really important to think about this spatial data as being a sum of some potentially smooth process plus something that's very rough, like white noise. If you leave out the white noise process and you don't include it when it should be, bad things can happen. So it's important just to put it in the model. So just to review here, the parameters we have are the variance of G, its correlation range, which I'm calling theta, and then also the variance of this white noise process. Now, it turns out, just as a technical detail here, when you're doing maximum likelihood or when you're estimating these parameters, it's really just enough to estimate the correlation range and this ratio of the variance of the white noise to the smooth process. And then you can back out sigma and tau squared easily from knowing theta and lambda. Now, if any of you have bumped into splines, this lambda is the same as the smoothing parameter in splines, which is called lambda. So very pivotal parameter here. No surprise that it's important. All right, so there's our model. If you're new to spatial statistics, or this should also be an introductory talk. I just wanted to remind you what the likelihood is, and then I'm going to show you some pictures. So just hang on through this slide, and we'll give you a little bit more intuition about what this stuff is all about. Okay, so here's the likelihood, and let me just remind you that here's our parameters: sigma, theta, tau. This y here, in our case, is going to be a 16 by 16 grid, 256 spatial observations. If we try to maximize this, looking at this, I realized I missed a minus sign out front here. This maximum doesn't have a closed form in all the parameters, so we're going to have to do this numerically. Now, for one grand challenge in spatial statistics is to try to deal with this likelihood for very large data sets. And so, I'm really dealing with many small problems here, but imagine that instead we wanted to do the whole problem at once, all 13,000 locations. Then this particular matrix would be a 13 by 13,000 matrix. We'd have to find a similar determinant of a huge matrix like that. This is a different kind of computational problem, and it's the kind that Matthias is one of the experts on, and he'll tell you all about how to solve those kinds of things. And I just wanted to emphasize that I am not using neural nets to solve that problem. Probably things like the Vecchia approximation or other kinds of fixed rank Kriging and basis functions are the way to approach that. Okay, so that's what we're going to be working on here. Let me just give you an idea of what these things look like. So all I'm doing here is I'm varying the white noise variance, that's tau squared. We're fixing the variance of the process at 1, and I'm just showing you what 16 by 16 fields look like. So as we go down in this direction, we're increasing the correlation range, and you can see that when we don't have much white noise added to the process, you can sort of see how there's more long scale structure as we increase the correlation range. And so obviously, if we're simulating fields, which is the whole point of this climate application, we want to get this right. Simulating climate sensitivity fields that look like this are going to be very different at a regional scale than ones that simulate like this. In addition, adding in white noise makes a difference too in the appearance of the fields. Obviously, there's a lot more heterogeneity, less coherence when we add in a large white noise variance on the field. And notice that persists even when we're in the situation where the smooth component is actually quite smooth. Adding in a lot of white noise sort of conceals that. Okay, so there's a classical summarization of spatial fields called the variogram. And I didn't want to write down the formula for this. Let me just talk through what it is. We have 256 observations, 256 spatial observations. I'm going to take all possible pairs of those. So 256, choose 2. I'm going to find the difference between each of those data values. So I'm going to have 256 choose 2 differences. I'm going to square that and then just divide it by 2. Observations that are far apart in distance are going to have a squared difference that's going to tend to be large on the average. And in fact, the expected value of that squared difference is 1-to-1 with the covariance function. So if I find this expected value, which we call the variogram, we can back out what the covariance function is as a function of distance. If we have the covariance function as a function of distance, I can tell you what the variogram is. Now, what I'm showing you here is those same 9 spatial fields, but I've computed the variograms for them. So what we have here is all these different pairs of points, 256 choose 2, their difference squared, plotted as a function of their distance of separation. And so you can see that for cases where there's a little bit of white noise added, there's substantial variability in these. These black lines here are the average values across the different distance classes. So here's here's a part of the talk where I just wanted to articulate sort of an open question here. So variograms, fitting them directly, have turned out not to be very good for estimating covariance parameters. However, there's something about the variogram where I sort of feel that it contains almost all the information you need. We just need to know how to extract it well. So in sort of more math stat language, the variogram of a data set, or the average across the distance classes, and maybe another statistic that indicates the variability, could be almost a sufficient statistic for these covariance parameters. And so that would be quite valuable if all this works out, because the variograms are fast to compute, they're easy to manipulate, and if they are almost sufficient statistics for these parameters theta and tau squared, we can use them in place of the original data. There's sort of a thread in Bayesian statistics where the Bayesian analysis is focusing on statistics of the data as opposed to working with the raw data itself. And working with the variograms would be in that kind of spirit, although I'm not doing a Bayesian analysis here. All right. Okay, so here's the neural net setup. We're going to do something very simple, and maybe, I don't know, it's so simple it just seems weird and confusing. I'm going to simulate close to 1 million Gaussian fields of different covariance parameter settings, and it turns out simulating 16 by 16 Gaussian realizations, the kind that I showed you in that block of 3 by 3, it happens extremely fast. I'm looking at about 40,000 different combinations of these covariance parameters. So that would be the correlation range and this parameter related to the variance is lambda. So we're covering a very sort of exhaustively the space of sort of reasonable parameter values that we expect. It looks a little strange here because I'm actually adjusting the values of lambda based on the correlation range. And that turns out to be an important thing to take into account. So that gray area, imagine we're simulating many fields across at all those different gray parameter values. We're going to fit a neural network to each of those fields to use those fields as training data. And we're going to fit this neural network to match the true values of the covariance parameters that we use to simulate. So in some sense, this is a huge Monte Carlo exercise where we're generating 1 million spatial fields. We know what the covariance parameters are for all those spatial fields. And we're simply finding an empirical way to match those fields as raw data or as the variogram to the true parameters. We don't expect to beat maximum likelihood, because maximum likelihood is basically as good as you can do. What we're hoping is that we're going to do as well as maximum likelihood, but do it much faster. And in fact, that's the whole take home of this talk, is we can train these neural nets to sort of be as good as maximum likelihood, but evaluate more quickly. Okay, so in machine learning, in neural nets, there's always this setup where we have a training sample that we use for fitting the data, and we're doing all kinds of things to sort of try to tease out the best parameters of that. Once we have that model that basically maps data to an estimated set of parameters, we then test it on a completely independent field. And I'm just mentioning that here is that we're evaluating these neural nets on 10,000 fields that are drawn from this parameter space. That's a subset of the original training space. We could do more than 10,000 fields to really nail down exactly what the accuracy is. To be honest, we only did 10,000 because it was sort of less to sort of deal with and less to plot and interpret. But we could have easily done 1 million there as well. Okay, neural networks. So here's an example of 4 inputs, and each of these inputs is going to a neuron. So you can imagine that this neuron is collecting 4 numbers. It's finding the linear combination, a particular linear combination of these numbers, and then applying a nonlinear transformation. The nonlinear transformation in this case, you can think of it sort of like a logistic function or sort of a step function. Technically, we're using the rectified linear function, but it's basically a nonlinear transformation. Okay, so this is one. I'm sort of trying to give you an idea of one layer here, but notice that we have 3 different neurons in this layer. Each of these is applying a different linear combination to the same inputs that are being supplied here. Okay, so the way this is made into a more complex model is, in this case, we have 3 inputs. They're sent to 4 neurons. And now the extra bit, the thing that makes these neural nets important or special, is we take the output from each of these neurons, and that becomes the input for another layer of neurons. And so let me just walk you through the counts here. So this particular neuron is receiving 3 inputs from the data, in this case, the input layer. It's applying a linear transformation to these, and then a nonlinear transformation. That's that output that gets sent here. These other 3 neurons are doing the same thing, although they're using a different linear transformation of the data that they're receiving. Okay, so these neurons now, this guy has the 4 inputs from this previous layer. It also takes a linear transformation of these, applies the nonlinear transformation, and then sends that on. And so I've just sort of counted up sort of what the parameters are here. The parameters that I'm counting is this linear transformation that each neuron applies to its inputs. The nonlinear transformation actually can stay fixed, which is convenient. So notice that in this simple network here, with just ostensibly 3 data points, we're actually making up, let's see, this is 16, 36 plus 5, 41 parameters we can actually put in this, which is tremendously overkill, tremendously over-parameterized. The interesting thing about deep learning is that these deep nets have training procedures where they're not afraid of having lots of parameters. And there are ways of sort of controlling the overfitting, being able to throw almost as many parameters as you have data points at a problem, and sort of controlling all that. Now, keep in mind that what's keeping us honest here is that we're training these networks on a particular training set. We're validating them on a completely independent set. So if our training overfits the data and is actually an awful model, we'll see that on the test data set. The other thing to keep in mind for this statistical application is I want to remind you what the target is. We're just trying to do as well as maximum likelihood. We know exactly the parameters that we want to fit. Our test sample and our training are completely unambiguous. We're simulating spatial fields from covariance parameters, and we simply want to recover those parameter values. Okay, there's another version of a neural net, a convolution neural net, which is particularly well suited when we're just going to supply the raw data to the neural net. And so this is a little bit of a depiction of how these convolutional neural nets work. So what we're going to do, say, for example, is we're going to take this 3x3 block of the spatial field, and we're going to apply a linear transformation to it, and that's going to give us this value right here. We're going to apply that same linear transformation to another 3x3 block, and that's going to be the value here. And so, you know, if you think about how this geometry works, we have 4 3x3 blocks that we can apply the linear transformation to. And so the net result is we're going to take this image and transform it to just a 2x2 image. And we're applying, in this case, the same linear transformation at every one of these 3x3 things. Okay, so the way this gets elaborated, the way we sort of generate more parameters is we say, well, if you like applying the linear transformation and then taking the nonlinear transformation, if you like doing that, why don't you do it a lot? And so, for example, in our particular case, we're actually doing 128 separate cases of this. So the way to think about that is that I'm just showing you the result of doing this once, and you can imagine taking a different linear transformation of this 3x3 box and getting another 2x2 image, and do it again and again. And so we're actually doing that 128 times. So that's how the convolutional neural nets end up getting sort of rich in their parameters. Okay. So this is just to remind you of what the basic functional step here. And, you know, I should say that in terms of learning this, in terms of thinking about it as a statistician, there's nothing mysterious really about these neural networks. We're basically taking our inputs, linear transformation, nonlinear transformation applied to that, and then our output from one layer now becomes the input for the next layer. So this composition makes things sort of complicated and difficult to write down. But in the end, we're just sort of iterating these functions. And the actual parameters of the model, well, here they are. They're just this linear combination of what our inputs are. All right. Okay, so the story behind this project is this is collaboration with Florian Gerber, who is a brilliant computational statistician. However, we started this off by me just trying to do a few things in R. I was using the Keras interface for training the nets in R. I did a fairly small problem, got it to work, presented it at JSM last year. I felt pretty proud of myself. And then I was talking to Florian about this, and I said, you know, I think this can work a little bit better than I did it. You know, it just needs a little bit more expertise on the deep learning side. Florian took this over and he did amazing work. Some of this he did using multiple cores, using cloud computing. He also migrated parts of this over from R into Python. And what I want to present in this table is basically Florian's production solution. And in fact, this works so well, you'll see in the results of the next page. it's actually very difficult to tell the difference between the approximation of these neural nets and the actual maximum likelihood estimates.
Doug, I have a quick question, just to make sure I understand. Are you actually putting in the 16 by 16 image here to the neural net, or are you putting in the variogram?
I'm doing both.
Oh, okay.
Because I was curious to see how both of them work.
Oh, so you did separately one and then separately the other. Okay.
Yep. The convolutional neural net really only makes sense for the images.
Right.
The actual variogram image fits this sort of dense network architecture where you just basically blast it out with lots of neurons.
Okay, thank you.
Yeah.
Hi, Dr. Nychka. Can I also confirm, just to verify that, so for the variogram-based approach, are you using the whole, variogram point cloud, or just that mean function as an input?
We are just using the mean function.
All right.
Yeah.
Okay. Thank you.
Yeah. For that 16 by 16 image, there are 119 unique pairwise distances. And so we're basically just putting in those averages over those 109 unique distances. Yeah. So input for one is 256. The input for the other is 119. Yeah, good questions. Okay, so here is Florian's final network. So we start, and this is the convolutional neural net one. We start with our 16 by 16 image. We do one convolution, which results in 7 by 7 filtered images. So we can think of these as the output images from this. And we have 128 different flavors of these, because we're actually estimating 128 different linear combinations. To these, we apply another convolution, and again, another 128 separate linear combinations. These are going to arrive in 3 by 3 images. At this point, we collapse these into just 128 outputs. And then we switch over and we use the dense neural net architecture here to take these 128 inputs, feed them into 500 separate neurons. And then finally, the results of these 500 neurons are combined to give us an estimate of theta and an estimate of lambda. About 600,000 parameters in this. And I just wanted to walk you through this particular layer just so that you understand how these parameter counts go. So at this particular layer, these neurons, each neuron is receiving 128 inputs. And so they have to estimate 128 plus 1 parameters for the linear combination, including just a constant. And of course, we have 500 neurons here. So the total number of parameters in this layer is 129 times 500. So you can see how the number of parameters grows quite a bit. Now for the variogram, we have a simpler architecture where these 109 values of the variogram are simply fed into a dense network. I think we finally arrived at around 1,000 neurons, and then those are fed into another 3,000 neurons. And then finally at the output level, those are distilled into just the estimate of theta and the estimate of lambda. Okay, so lots of computation here. I think you don't have to go as extreme as this in terms of a huge network architecture. My initial pilot of this project, just working in R, I could train things a lot quicker I wasn't getting as accurate results, but I think there's some kind of compromise there where we don't have to go to this this huge thing. However, you know, I should point out that once the network is trained, once you've estimated these 600,000 parameters, you're done. And any 16 by 16 problem, you just pull out this network and use it. So it's sort of basically a one-shot thing. And really the number of parameters is all hidden to you. You're simply just evaluating the network, which goes very fast. Okay, so here are the main results of this talk. What we're doing here is across estimating lambda. I'm showing you box plots of the variation between the our log estimate of lambda minus the true value. So if we were getting perfect estimates, we would see everything at 0 here. This is the scatter for using the raw image. This is the scatter for using the variogram. And here are the MLEs. So you can see that the MLEs have a little bit more variance here. I think that if we went into the subtleties of these, we would see these are slightly biased. And so what we're having here is a trade-off between variance in the MLE and bias in our neural net estimates. Okay, so that's for lambda. For the range parameter, you can sort of see sort of similarity. The images based on the neural net are estimating parameters about the same as the maximum likelihood estimates. What I like about this application of deep learning is, as I've said before, we know what our target is. We know what our goal is. We simply want to estimate these parameters as well as MLEs. And we have the facility through the Monte Carlo simulations to create very large training sets, very large validation sets, so that we can actually be sure that we've done that. Okay, so just to follow up in our application, what I'm showing you here is the estimates of the log lambda parameter, MLEs across our spatial domain. This takes about, let's see here. I have the timing in the next slide that I'll show you. But here are the MLEs. Here's the variogram. Using the neural net based on the variogram. And so we see that by and large, we get pretty good matchup here. A little bit of discrepancy, say like around Hawaii, but by and large, the same patterns. Now keep in mind that the MLEs themselves have uncertainty attached to them. They are statistical estimates of the covariance. So, you know, we if there are discrepancies between these, we also want to take into account that there's some sampling error here. Anyway, so so that's how they compare. In terms of the timing, training the network took about 2 to 6 hours, depending on how many passes you want to go through the data, the accuracy. In terms of the timing to evaluate them, though, it took on the order of tens of seconds for the convolutional neural net and about 2 minutes to produce that plot that I just showed you. If we were going to fit these estimates by maximum likelihood, Florian actually did this in a slightly different way, but I estimate it'll take about 1.5 hours to get all these estimates in a rigorous kind of way. So we're talking about, would you like these estimates in 2 minutes, or would you be willing to wait for 1.5 hours? And I would argue, again, if you're getting these estimates that are approximate, but you know basically what their error properties are, if you're getting them within 2 minutes, you're going to do a lot more exploratory data analysis than if you have to wait an hour and a half. And actually, for an old guy like me, if I have to wait an hour and a half, I often forget actually what I was thinking when I ran this. So it's better to get things back quickly. All right. So just to round up here. So some things to explore. How do we adjust the variogram for different numbers of observations in the bin counts? And the side story here is that, yeah, equally spaced data on a regular lattice, it's important, but the real the real treasure to sort of work out here is, can we make this work for irregular data? And the variogram has the property where we can find it for irregular data, although it's not going to have as nice nice sort of comparable sample sizes in the bins from one sample to the next. So there's a little bit of work to do there. So I work with this lattice-Krieg model, which is a spatial auto regression. It's actually difficult to fit the lattice-Krieg model locally to Windows. It's a little bit slower. So I'm thinking about just using the neural net to get the estimates for the lattice-Krieg model. And you could also think about doing this if you're thinking about Vecchia approximations to the covariance. You could also think about schemes also where the neural nets could inform directly those values for the precision matrices. You could expand this to be, rather than just the MLEs, you might think, it's often nice to have standard errors. Are there ways to trick these neural nets into also computing those for you? And then finally, and I would say this is also a very active area of computer science, to the extent that we can, to understand why these work. And I would say in this case, we would sort of try to find the numerical analyst who actually devised all these coefficients. We can't ask the neural net what they're doing, but there's some sense that the neural nets are doing something a little bit more fundamental, and so that's a way to get at this. All right. So I'd like to thank you for your attention. Again, I'm really sad that I can't be there in person, and I hope that we'll be catching up either at meetings or I can get out to College Station soon.
Okay, so thank you very much, Dr. Nychka, for a nice talk. So if anybody has any questions for Dr. Nychka, please just go ahead.
Can I ask a question?
Yes, sure.
Hi, this is Irina Gainanova. Very nice talk. Really enjoyed it. I'm not an expert in spatial statistics, but the question that I had is, when you train your neural nets, you create the training data that exactly follows the model that you want to fit.
Yeah.
But in practice, when you do the maximum likelihood estimation, you probably do it on the data that doesn't actually exactly follow that model. So what I'm wondering is whether the discrepancy that you get between the neural nets and the MLEs is due to the fact that the data is not coming from that model.
Oh, that's a great question. I hadn't thought about it that way. Yeah. When I was looking at that data, I always just assumed that the data is coming from a perfect Gaussian field, and we're just
exactly.
seeing. Yeah. So how would you get at that? So the brute force approach is, of course, in your training, you can train your neural net on things that aren't quite Gaussian, have a little bit of departure in the model, and and sort of build in all of that. And of course, you'd have to make lots of choices
Right,
as to how you
right.
would build that in.
I mean, you
But-
can do a very data-driven approach. Like if you believe the MLE is true, if you want to really target the MLE, you can just do data sets, evaluate MLE on a given data specific 16 by 16,
Yeah,
and then
yeah.
use that. So
Yeah.
that's essentially fitting the likelihood maximizer function then, correct?
Yeah. You know, I thought I've thought about that as an alternative, and maybe Florian and I will play around with that. So I think what you're suggesting is, I made this big speech about we have training data and we're trying to get the true parameters. Why not try to recover the MLEs? I mean, if you really want the MLEs, just train to get them. The reason we didn't do that initially is that if we have 1 million training samples, then we actually have to find 1 million MLEs.
Yeah, that's what I thought.
And at that point, it gets a little bit redundant, because, you know, we're sort of complaining about, oh, we can't find all these MLEs, but then we turn around and say, okay, but we're going to find them to train. So
No,
yeah.
I understand. Yeah, I was just thinking when you showed it on the data, because it was a more significant discrepancy, I feel like, that one would expect in those couple points.
Yeah.
And I wonder if that's why.
Yeah. Part of the discrepancy has to do with the fact that over the ocean, these climate fields are very smooth. And so the variance of the white noise process is very close to 0. And so the issue is if you estimate that as 10 to the minus third or 10 to the minus second, it doesn't really matter. However, on a log scale, those are big differences.
Right.
To a climate scientist, they would basically say, look, it's basically 0. So, you know, get on with it. Yeah.
Thank you.
Great comments, Irina. Yeah. Yeah. And I would argue no one is really a total expert in spatial statistics. It's sort of too big, and there's too many things going on. So we're all part of your club.
Okay, any other questions for Dr. Nychka?
Hi, thanks for the great talk. I had a quick question about periodograms, and I was wondering what you thought about the interpretation that the neural network is doing something like a transform and then fitting or estimating the parameters from those sort of spectral or periodogram values.
Well, the honest answer is I don't know what the neural nets are doing. You know, I'm running them as a black box. Besides the variogram, another possibility is to compute the spatial periodogram and use that as the raw input. That may be a little bit more stable. And I've recently become aware that there's actually equivalent fast Fourier transforms for irregularly spaced points. So, you know, that may be a nice possibility.
Okay, thanks.
Yeah, maybe easier also, you know, so I have this idea with irregular data, you want to give it the variogram or the periodogram, but also give the net some additional information about the variance of each of these things, because it'll be irregular if you have irregular data. The periodogram may be easier to sort of quantify that than the variogram. So yeah, good question. I wish I knew the answer to it.
Okay, I guess that's probably the time to end the seminar. So let's thank our speaker again. Thank you very much for this very nice talk, Dr. Nychka.
Okay.
And I hope that we're gonna have you visit physically in College Station.
Yeah.
Okay, so I guess that's it. Thank you, everybody. and
Okay.
see you again next week. Bye.
Yep. Bye-bye,
Thanks, Doug.
everybody.
Bye-bye.
Bye.
Yeah.
Thanks for attending.
Yeah. Bye.